So, hi everyone, I'm Zirui from UVA. Today I'm going to talk about ZipLLM, a storage system designed for large language models. The core idea is to combine model-aware deduplication and compression in a synergistic way. This is a joint work with my lab mates Tingfeng, Zhaoyuan, and my advisor Cheng from UVA, together with Juncheng Yang from Harvard. So let me start with a trend. This figure shows the total number of models and the total storage size on Hugging Face over the past few years. You can see from the 2023 to 2025, the total storage on the model hub grew from 0.28 petabytes to over 77 petabytes. That's an exponential growth, about 275 times in just 2 years. So if this trend continues by 2027, model storage alone will reach the exabyte scale. So we are facing a model storage crisis. On one hand, users keep uploading fine-tuned models to the model hubs. On the other hand, trainers keep saving massive checkpoints across different steps, runs, and versions. So together, the storage demand is simply unsustainable. This motivates us two questions. First, what are the actual characteristics of LLM storage? And second, can existing data reduction techniques keep up with this growth? With these two questions in mind, we did a large-scale study. We collect all the LLM repositories from Hugging Face and conducted, to the best of our knowledge, the first large-scale field study of large language model storage. From this study, we got two key observations. The first one is the fine-tuned models dominate. In this figure, the solid lines show cumulative storage size, and the dashed lines show the cumulative model count. Blue is for the base models, yellow is for the fine-tuned models. You can see that the yellow lines grow up exponentially after 2023, while the blue lines just stay almost flat at the bottom. So in fact, there are only about 20 widely used open source based models like Llama, Mistral, Q1, DeepSeek, and so on. But the number of fine-tuned variants is growing much faster. While in terms of total storage, the fine-tuned models dominate the model hub. So the first insight we get here is very simple. Fine-tuned models drive the storage cost, and that's where optimization should focus. The second observation looks at how fine-tuned models relate to their base models. The top row shows 3 models fine-tuned from Llama 3.1 8B. The bottom row shows the 3 models fine-tuned from Mistral 7B. For each one, we compute the weight delta against the base model by using this equation. The delta is fine-tuned models' weights minus the base model weights. Let's look at the top row first. You can see the deltas are tightly centered around 0, and the range is very narrow. This tells us after fine-tuning, most of the base model weights are barely changed. But if we instead compare Mistral fine-tunes against the Llama base, the picture can change completely. Look at the bottom row. The deltas are much wider from 0 to 5. So across different families, the differences are huge. But also notice something interesting. The 3 Mistral fine-tunes, even though their deltas against the Llama are huge, they all share a very similar distribution. So that tells us the 3 Mistral models are actually close to each other. So to visualize this more clearly, we built an LLM family graph. We use a metric called bit distance to do the clustering. It's the average number of differing bits when you compare two model weight by weight. You can see that within a family, model cluster very tightly across different families. There is a clear separation, although the related families like Llama 3 8B and the 3.1 8B appear close to each other. So this gives us the second insight. Bit-level similarity is a robust signal for clustering LLM families, and the models that are close in bit distance are great candidates for delta compression. So with these two insights in mind, let's look at how Hugging Face does storage reduction today. It's a three-step pipeline. First, it uses the file deduplication. It removes identical model files across repos. And second step is chunk deduplication. It uses rolling hash to identify chunks and remove the duplicate chunks. And the third one is optional step. It applies lossless compression on the remaining chunks by using ZipLLM or ZSTD compression algorithm. But when we apply this traditional design to Model Hub, two clear problems show up. First, the CDC is inefficient for LLMs. Across millions of models, it will generate billions of chunks, so the index becomes huge and lookups are slow. And within a single file, processing is sequential because of rolling hash. There is no parallelism. The second problem is existing compression algorithm is not LLM aware. It compresses each file independently, ignoring the redundancy across different LLM families, models, and it's also byte oriented. It ignores the floats, the tensor structure inside the model weights. As a result, the delta compression ratio is really only 10 to 20%. So based on our two insights, we redesigned the Model Hub storage pipeline. Two main ideas here. First, we do the deduplication by tensors, not chunks. And second, we design a LLM-aware delta compression. We call it BitX. Let's start with tensor deduplication. The modern model formats like SIF tensors or GGOF already have clean tensor boundaries built into the file. We use these boundaries directly. So the metadata becomes 3 orders of magnitude smaller than chunk-based indices. And since tensors are independent units, we can dedupe them in parallel. It gives much higher ingestion throughput. So now let me introduce the BitX, our compression algorithm. The idea is very simple. Fine-tuned model is mostly similar to their base, so we don't need to store everything. We only need to store the change or what changed. Take a float 16 as an example. It has 3 parts: a sign bit, an 8-bit exponent, and a 7-bit mantissa. When weight changes only slightly during fine-tuning, the exponent usually stays the same. So when we XOR 2 floats, the exponent usually always cancels out to 0. And only a few bits in the mantissa actually flip. So the overall XOR result is a delta full of zeros, which is extremely easy to compress. For each pair of corresponding float point values in base and the fine-tuned models, we do the XOR. We compute the XOR. Next, we apply lossless compression on the delta. In this paper, we use the STD. Yeah. Instead of compressing the whole delta as 1 byte stream, we split it by field, like sign plus mantissa as 1 part, and another part is 8-bit exponent. And this gives us much better compression ratio. Now, let me put everything together. This is how ZipLLM works. The first step, we run file dedupe and tensor dedupe on the uploaded models, and we only keep the unique tensors. Then, for the remaining tensors, we use bit distance and information from model cards to cluster the models and build an LLM family tree. This tells us which fine-tuned model should be paired with which base for the next step, the delta compression. Step 3, following the family tree, we apply BitX between each fine-tuned models and its base. The output is a set of compressed tensors. So in the evaluation, we collect 1,700 LLM repositories from Hugging Face, covering Q1, Mistral, Llama, and Gemma family models. And we use an EC2 instance to do the evaluation. Here is the overall result. The x-axis is data reduction ratio. The y-axis is throughput. Up to the right is better. The throughput here is how fast each model, each method can ingest and reduce incoming model data. To make the comparison fair, we run all the methods on the same machine with multi-threading enabled across all available CPU cores. You can see the BitX and the ZipLLM both land in the top right region and clearly outperform the existing methods. Let's also zoom in on compression methods alone. The y-axis is data reduction ratio. The ZSTD and the ZipNN mostly sit between 22 and 30%. The BitX has a median around 50%, and a large portion of cases reach near 16% or even higher. So our code is open source. This is a quick demo comparing the two methods. As you can see, the BitX achieves near 10 gigabytes per second, but the ZipNN already only achieves 1 gigabytes per second. Yeah. To wrap up, first, modern AI platforms really need a storage system designed for AI workloads. Second, our large-scale study reveals key sources of redundancy in LLM storage. And third, ZipLLM achieves significantly higher storage savings and throughput compared to shorter approaches. And the upper QR code is this work, ZipLLM. The bottom one is our new work on model storage, which achieves 70% data reduction ratio, 20% higher than this work, ZipLLM. So that's all. Thank you. Happy to take any questions.